In this video, we are going to look at the graphs of polar equations. The graph of an equation in polar coordinates is the set of points r theta that satisfy the equation. In our first examples, we focus on some of the more structurally simple polar equations. In each of these examples, only one of the variables r and theta is present, making the other variable free. This makes each of these graphs easier to visualize than others. In the equation r equals 4, theta is the free variable. The graph of this equation is all of the points of the form 4 theta for any choice of theta. This would describe all the points that are 4 units from the origin. It would be a circle of radius 4. Similarly, r equals -3 square root of 2. The solutions of this equation would be all the points of the form -3 root 2 theta. For positive values of theta, having a negative radius will reflect our points to the bottom half of a circle. For values of theta between pi and 2 pi, our negative radius will describe all of the points on the top half of a circle. Thus, the equation r equals -3 root 2 is the equation of a circle with radius 3 square root of 2. In the equation theta equals 5 pi over 4, r is the free variable. So all of the points of the form r 5 pi over 4 will be solutions of this equation. With an angle of 5 pi over 4, we have a rotation that takes us into the third quadrant. For positive values of r, we would live on this side of a line. For negative values of r, would be reflected around the origin to points that would live on this side of a line. Lastly, in the example theta equals -pi over 6, we'd be talking about points of the form r -pi over 6. The rotation of -pi over 6 would bring us down into the fourth quadrant. For positive values of r, we would live on this side of our line. For negative values of r, we'd be reflected around the origin to points that lived on this side of a line. Let's look at a more interesting example. Suppose we wish to graph the equation r equals 6 cosine of theta. A reasonable way to start is to treat theta as the independent variable, r as the dependent variable, and evaluate f of theta at some friendly values of theta, and then plot them in the plane. We can generate the table below. For theta equals 0, we'd have the r is 6 cosine of 0, and since cosine of 0 is 1, this r is going to be just 6, and so we get the ordered pair 6, 0. For the angle pi over 4, we're talking about a rotation pi over 4 from the positive x-axis. We would find a radius of 3 root 2. At pi over 2, we'd find a radius of 0. At 3 pi over 4. Now 3 pi over 4 would be in this second quadrant over here. But our radius is going to be negative, and so it'll reflect around the origin to a point that's down here. At pi, we would be over here on this left half of the plane. We would again get a negative radius, which would reflect to the other side of the origin, back where we started. As we go through more values of theta, we retrace out other points that we've already seen. Notice that after finding 9 ordered pairs, we've only generated 4 points that live on the graph of our equation. This may be enough to make a leap of faith and think that our equation is going to be the graph of a circle that's been shifted 3 units to the right with a radius of 3. As an alternate approach, let's start by graphing one cycle of the equation in the theta r plane. 6 cosine of theta is a cyclic function with period 2 pi and amplitude 6. So we would start up here at 6, 2 pi later we would be at 6 again. Halfway in between at pi we would be at negative 6, and our graph would look something like this. Now in this graph, the y value, the r value, will always tell your distance from the origin. For a value of theta starting at 0 radians, we would have a radius of 6. 0 radians would be in this direction, and we would have 1, 2, 3, 4, 5. It would start right here. As our values of theta increases towards pi over 2, these distances become smaller and smaller. And so as we rotate through the angle 0 to pi over 2, our radius vectors become shorter and shorter and shorter until eventually at pi over 2, we'd be at the pole. As we proceed and go through angles between pi over 2 and pi, then on the graph of r theta, our radius vectors would be negative. And so all of the radiuses going from pi over 2 to pi would reflect back over into the fourth quadrant. As we approach an angle of pi, our radius vectors get longer until finally at pi they are the longest. And so once you rotate all the way to pi, our negative radius of 6 would reflect back to our starting point. As we continue to go through angles between pi and 3 pi over 2, our radius vectors would still be negative. So when you're in this third quadrant, they would reflect over into the first quadrant and trace out again the top portion of the circle that we already seen. From 3 pi over 2 to 2 pi, as we rotate through this fourth quadrant, our radius vectors will always be positive and getting longer. And so we notice that the graph of 6r, or 6 cosine of theta, is the graph of a circle that's been shifted 3 units to the right and has a radius of 3 units. In general, we can use this approach to graph a variety of polar equations. Here is a gallery of some of the more common polar equations we want to recognize. The equation of a spiral, of a circle with symmetry around the x-axis, a circle with symmetry around the y-axis, a lemniscate, a cardioid, a limacon with a loop. We can also create the graphs of roses, and we'll notice here that there are 2 different orientations of a rose depending on whether we're using a sine or a cosine function, but that these are only 90-degree rotations of each other. We can also look at the effect of changing the argument inside the sine function. And depending on the size of that factor, where n could be an even or odd number, will generate different numbers of petals on our rose. Notice that for n being even, 2, 4, or 6, that we'll actually have 2 n petals. If n is odd, 3, 5, or 7, then we'll just get n petals on our rows. Some of the other interesting polar graphs that we could create are here. They don't necessarily all have names, but some of them are interesting nonetheless. For example, the graph of a butterfly. We'll look at more examples in another video, but I hope this is helpful, and I'll see you next time.